Time travel has long been considered one of humanity's greatest dreams, a fascinating idea, often confined to science fiction, that continues to stimulate the collective imagination. But is it truly just a matter of technology, not yet advanced enough? Or does the universe itself impose insurmountable limits? Many believe that the impossibility of time travel is only temporary, linked to the current state of human knowledge. However, an analysis of the fundamental laws of physics suggests a more complex reality. It appears that the universe has imposed precise restrictions on time travel, perhaps to prevent paradoxes and contradictions that would undermine its coherence. And yet, despite these limits, some theoretical solutions continue to fascinate the scientific community. Among them, one of the most discussed is the hypothesis of using wormholes, space-time tunnels that, under certain conditions, could allow movement not only through space, but also through time. But how would such a mechanism actually work? To understand this possibility, it is necessary to start from the basics. Wormholes, also known as space-time tunnels, are hypothetical structures that would connect two distant regions of space-time, allowing almost instantaneous passage between them. The idea originated in the early 20th century, when physicist Ludwig Flamm first proposed the existence of such tunnels. A few years later, in 1915, Albert Einstein formulated the theory of general relativity. Within its field equations emerged a solution that suggested the existence of space-time connections. In collaboration with Nathan Rosen, this solution led to the concept of the so-called Einstein-Rosen bridges, the first theoretical model of what is now called a wormhole. From a mathematical point of view, therefore, nothing seemed to prevent the existence of these structures. However, historical events of the period, particularly the Second World War, interrupted research in this field for years. The topic returned to the forefront in the 1970s, when physicist John Wheeler demonstrated that wormholes, while theoretically possible, would not be stable if formed from ordinary matter. They would tend to collapse too quickly, making them unusable as traversable passages. It was Wheeler himself who coined the term wormhole, inspired by the analogy of a worm creating a tunnel inside an apple, shortening the path between 2 points on the surface. A major boost to the study of wormholes came in 1985, when Carl Sagan, while working on the science fiction novel Contact, was searching for a plausible way to allow the protagonist to reach the star Vega within a reasonable amount of time. His discussions with physicist Kip Thorne led to the development of theoretical models exploring the possibility of stable, traversable wormholes. Thorne identified a fundamental condition: the need for a form of exotic matter, characterized by gravitational properties opposite to those of ordinary matter. This matter, theoretically possessing negative mass, would be capable of keeping the wormhole open, preventing its collapse. These hypotheses, while remaining speculative, paved the way for numerous subsequent studies and deeply influenced scientific and cinematic imagination, as demonstrated by the film Interstellar. Once again, science and science fiction intersected, feeding into one another. However, exotic matter remains a purely theoretical concept. Some hypotheses link it to dark energy, responsible for the accelerated expansion of the universe, but no concrete experimental evidence exists. Moreover, the amount of energy required to create and maintain a stable wormhole would be enormous, in some cases even exceeding the total energy contained in the observable universe. To further complicate the picture, there is no known natural process capable of generating wormholes, unlike black holes, which form from the gravitational collapse of massive stars. This makes their existence even more uncertain. And yet, in theory, an extremely advanced civilization might have discovered a way to create this exotic matter and artificially construct a wormhole. If one were ever detected, an artificial origin would be a concrete possibility. Observing a wormhole, however, would not be easy. From the outside, it would appear very similar to a black hole. Only close observation could reveal its true nature, showing the other end of the tunnel as a distorted window onto another region of the universe. But assuming wormholes exist and are controllable, could they truly function as time machines? To answer this question, a thought experiment is useful. Imagine two synchronized wormholes. One remains on Earth, while the other is carried aboard a spacecraft traveling at speeds close to that of light. According to relativity, time aboard the spacecraft would pass more slowly than on Earth. If the spacecraft traveled for 1 year, 10 years might pass on Earth. Upon return, the two wormholes, though synchronized, would be located at different moments in time. Passing through them would make it possible to move forward or backward in time within very precise limits. This mechanism would allow real time travel, but not unlimited travel. It would not be possible to return to a time before the creation of the wormhole itself. Moreover, the duration and extent of the journey would depend on the spacecraft's speed and the time dilation experienced. In conclusion, wormholes represent one of the most fascinating hypotheses in theoretical physics. From a mathematical standpoint, they are possible. From a practical standpoint, they remain extremely unlikely. And yet, studying them continues to help physicists gain a deeper understanding of the structure of the universe, its laws, and its limits. For now, time travel remains confined to theory and science fiction. But the history of science teaches that what seems impossible today may one day prove to be surprisingly real.